Now we are going to discuss about the Taylor series and the Maclaurin series. So how we have seen that Taylor series can represent functions within their intervals of convergence. A fundamental question arises, given a function f, can we find a power series that represents it? So this is where the Taylor series and the Maclaurin series occur. So this series represent function as infinite polynomials whose coefficients are determined by the function's derivative at a single point. So this powerful idea connects differential calculus with infinite series and provides powerful tools for approximation. Now we have here a theorem. So if f has a power series representation or expansion at a, that is, if f of x is equals to summation of c sub n times x minus a raised to n, the absolute value of x minus a is less than r. Then, its coefficients are given by the formula c sub n is equals to f raised to n times a over n factorial. So, by substituting this formula for c sub n back into the series, we see that if f has a power series expansion at a, then it must be of the following form. We have here f of x is equals to the summation of f raised to n times a, f of a raised to n over n factorial times x minus a raised to n equals to f of a plus the first derivative of f of a over 1 factorial times x minus a plus the second derivative of the f of a, and then it becomes over 2 factorial x minus a squared plus the third derivative of f of a over 3 factorial x minus a raised to cube plus so on and so forth. So if the degree of the derivative is going to the second, then the denominator is also 2 factorial. Same with the other. And if the series in the equation 6 is called the Taylor series of the function f at a, or about a or centered at a, for the special case a is equals to 0, the Taylor series becomes f of x is equals to summation of f of 0 raised to n over n factorial times x raised to n is equals to f of 0 plus first derivative of f of 0 is equals to 1 factorial because it is in the first degree plus the second derivative of f of 0 over 2 factorial because it is in second degree, and so on and so forth. So this case arises frequently enough that it is given the special name Maclaurin series. Now let's have an example. So find the Maclaurin series for f of x is equals to e raised to x and prove that it converges to e raised to x for all x. So for our solution, we need to compute the coefficient c sub n is equals to f of 0 raised to n over n factorial. So for f of x is equals to e, all derivatives are f of x raised to n is equals to e raised to n. So f of 0 raised to n is equals to 1 for all n. Therefore, the Maclaurin series is summation of 1 over n factorial times x raised to n is equals to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial plus so on and so forth. To show this converges to e raised to x for all x, we examine the remainder term. So using Taylor's inequality, we can show that the absolute value of r sub n x is less than or equal to m times the absolute value of x raised to n plus 1 over n plus 1 factorial, where m is bound on e raised to x. Since limit of n approaches to infinity, absolute value of x n raised to n plus 1 over n plus 1 factorial is equals to 0. For all x, we have limit of n approaches to infinity, or sub n x is equals to 0 for all x. Therefore, the Maclaurin series converges to e raised to x for all real numbers. So e raised to x is equals to the summation of x raised to n over n factorial is equals to 1 plus x raised to 2 over 2 factorial plus x raised to 3 over 3 factorial plus x raised to 4 over 4 factorial plus so on and so forth for all x. Another example will be find the Maclaurin series for f of x is equals to sine x. So for our solution, we compute the derivatives and evaluate at 0. So we have f of x is equals to sine x, f of 0 is equals to 0. So for our first derivative, we have cosine x, and our f of 0 is equals to 1. And for our second derivative, we have negative sine x as we base it to our first derivative, which is cosine x. And our second derivative for our f of 0 is equals to 0. Now for our third derivative, we have negative cosine x. We base it again to our second derivative which is the negative sine x. And our f of 0 in the third degree is equals to negative 1. And for our fourth derivative of f of x, we have sine x again. So we have here f of 0 in the fourth degree is equals to 0. So the pattern repeats every 4 derivatives. So the coefficients are c sub 0 is equals to 0 over 0 factorial, which is 0. And c sub 1, which is 1 over 1 factorial, is equals to 1. C sub 0 is equals to 0 over 2 factorial, which equals to 0. C sub 3 is equals to negative 1/3 factorial is equals to negative 1/6. C sub 4 is equals to 0 over 4 factorial, which is equals to 0. So we have C sub 5 equals to 1 over 5 factorial is equals to 1 over 120. So take note that the factorial is only applicable on the denominator and not in the numerator. So therefore, the Maclaurin series is x minus x cubed over 3 factorial plus x fifth over 5 fifth factorial minus x raised to 7 over 7 factorial and so on and so forth. So we have summation of negative 1 raised to n is equals to x raised to 2n plus 1 over 2n plus 1 factorial. Therefore, this series converges to sine x for all real numbers x. We have here another example. Find the Taylor series for f of x is equals to ln x centered at a is equals to 1. So for our solution, we compute the derivative and evaluate at 1. So f of x is equals to ln x, f of 1 is equals to 0. For our first derivative, we have f of x is equals to 1 over x, f of 1 in the first degree is equals to 1. So f of x in the second derivative, we have negative 1 over x squared. So we have f of 1 in the second degree is equals to negative 1. So in our third derivative, we have 2 over x cubed, which is the f of 1 in the third degree is 2. And our fourth derivative is equals to negative 6 over x raised to 4. So our f of 1 in the fourth degree is equals to negative 6. So the pattern is f of x raised to n is equals to negative 1 raised to 1 minus n minus 1 times n minus 1 factorial over x raised to n for n is greater than or equal to 1. So f of 1 raised to n is equals to negative 1 n minus 1 times n minus 1 factorial. Therefore, the Taylor series coefficients are s c to the 0 is equals to f of 1 is equals to 0. So this is the representation. Therefore, the Taylor series is summation of negative 1 raised to n minus 1 over n multiplied to x minus 1 raised to n is equals to x minus 1 minus x minus 1 squared over 2 plus x minus 1 cubed over 3 minus x minus 1 raised to 4 over 4 and so on and so forth. So this series converges to ln x for 0 for x greater than 0 and x less than or equal to 2. So that would be all for our Taylor series and Maclaurin series. Thank you and God bless.